Welcome, honors students. Today we're going to actually begin 14.3. We spent just over a week in 14.2. We talked about Boyle's Law, Charles' Law, Gay-Lussac's Law. In our last virtual lesson, we learned about the combined gas law. So now we're going to move into a new area where we're talking about the ideal gas law and then what an ideal gas is. So we're going to actually be utilizing that combined gas law and doing one thing differently. We're going to change moles, the amount of substance that we're talking about. So we'll see how we actually work those type of problems. So welcome as we start 14.3. So we start off with a case file all the time here. We talk about this fog. It's used in restaurants. It's used to set up an ambiance in a lot of decor. So here you see this foggy substance, and we learned what that was. That's actually solid carbon dioxide, and it's going through a process called sublimation, where it goes directly from solid to gas. And that is has a lot of practical uses. So the ideal gas law. So how can you calculate the amount of a contained gas when the pressure, volume, and temperature are specific? So we're talking about amount of a contained gas, so we're talking about moles. Well, we already learned about moles and a gas. We learned that 1 mole of any gas equals 22.4 liters at STP. And we learned that STP is standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere. So that was STP. And we learned that previously. So now we're going to learn how we can vary this temperature and pressure and determine any of the other factors based on the ideal gas law. It's very useful. The ideal gas law that we're going to learn about actually gets very complicated, but we're not going to look at it in its most complicated format. We could calculate molar mass, we could calculate mass, we could calculate density off of this same formula. We're not going to go that far in depth. We're going to stay at the surface level and learn how to calculate it. We're going to look at several examples today. So quickly going through this, I'm not going to spend a great deal of time looking at exactly how they derived it, but I am going to just at least go through this process. Suppose you want to calculate the number of moles, and the moles is going to be represented by N. We've already looked at that previously, but N is going to be the moles of gas in a fixed volume at a known temperature and pressure. So understanding that volume depends on the number of particles. Well, we already knew that the volume of 1 mole at STP is 22.4 liters. So if you change the moles, the amount of substance, you're going to change the volume. So the number of moles is directly proportional to the number of particles. And therefore, it must be directly proportional to the volume. And that's what this is stating down here. So you can interpret moles in the combined gas law by adding N to it. So we're going to introduce moles to this combined gas law. So here you notice our combined gas law here at the bottom. You recognize this from our last virtual lesson. PVT equals the final PVT. And what did they do? They added moles in here on the bottom. So when you talk about anything in the denominator being directly proportional, well, we know that it's directly proportional to the volume. So, and it would be directly proportional to the pressure, because the more you have, the higher the pressure would be. So that's why N has to be on the bottom. And how do we derive the combined gas law? Well, if you hold the moles constant, and that's what we said when we learned about the combined gas law, you just cancel off the moles. And it doesn't matter, but now we're not going to cancel off the moles. So if you know the values of pressure, volume, temperature, and moles, you can calculate this constant. the ideal gas constant. This is a new term that we're going to be introducing in this particular section. It's called R, and it's called the ideal gas constant. So how do they do that? Well, what they've done is they've taken this far side. If we pan this slide back, they take this part of this equation right here, and they set it up equal to R right there. And now they can plug in some information. So recall that 1 mole of every gas occupies 22.4 liters. We just talked about that at STP, and they changed it to kilopascals, which is fine. 101.3 kilopascals and 273 Celsius of Kelvin, sorry. So remember that it was 0 degrees Celsius. So you add the 273, and that gives you 270 Kelvin. That's where they get this from right here. So if you plug all this in here at the bottom, and that's what you're going to see right here. They plug all this information. That's how they derive this ideal gas constant. If you have your formula sheet, you have this particular one on your formula sheet. But this is not the only value of the R, because you can change your pressure to something else. There's actually 3 that you could use. We're not going to focus on 3. We're going to use the 2 main R constants. One of them is on your formula sheet, and I'm going to have you write the other one in, because you will need to know the other one as well. So you can write it off this virtual lesson and add that to your formula sheet. So if you notice here, you have your kilopascals. Kilopascals and atmosphere are your 2 main pressures when you deal with gases. So this is the R value that's on your formula sheet. 8.31 liters times kilopascals divided by mole kelvins. So if you change this to 1 atmosphere, and get rid of the kilopascals, and you plug that in your calculator, you're going to come up with the other R value I'd like you to write down. And it is R equals, and it is 0.0821, and this is atmospheres times liters divided by Kelvin times mole. So that is your second R value that you do need to write down. So please take a moment, pause the video, and write that down. All right, welcome back. Hopefully you did that, because it's important that you have both R values. So 8.31 and R for 0.0821. It depends on what your pressure's in. Kilopascals, it's the first. Atmospheres, it's the second. So you don't have to convert everything back to kilopascals. All right, so here is your ideal gas law. This is the formula that is on your formula sheet, and you will need to know how to use it, and that's what we're going to practice. So PV equals nRT. So we have pressure, volume equals moles, ideal gas constant, and temperature in kelvins. Please don't forget the temperature must be in Kelvin. All gas problems, the temperature has to be Kelvin. All right, so when the pressure, volume, and temperature of a contained gas are known, you can use the ideal gas to calculate the number of moles of gas. So let's look at an example. So at 34 degrees Celsius, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kilopascals. How many moles of nitrogen gas are in that tennis ball? So always write down everything that you need to know. And our pressure was listed in kilopascals, so right away we pull our R value that has kilopascals in it, and it's the 8.31. So you change your temperature to Kelvin, and then you write down your formula, and then they convert it. They change and divide it out so that they can have N isolated by itself, and then they just plug in everything right there, and you can see how your terms cancel off, and you plug in your calculator, you get moles as 1.23 times 10 to the negative 2 moles of nitrogen. And it does make sense when you look at the particular problem. So here's a checkpoint. Take a moment and look at this and see if you can figure this one out. It says, how would you rearrange the ideal gas law to isolate temperature? So anytime, always start by writing your formula down. So you have here PV equals nRT, and you want to isolate temperature. So you would divide by nR, both sides. That cancels off here, and that isolated your temperature. So when you look at this, which one is PV divided by nR? Well, it's C, and sure enough, it is C. All right, let's work a problem together here. When the temperature of a rigid container containing 685.0 liters of helium gas is held at 621 Kelvin, the pressure of the gas is 1.89 times 10 to the third kilopascals. How many moles of helium are in the container? So when I see this, I have one pressure, I have 1 liter, and it's asking me for moles. That's my clue, the ideal gas law. So I'm going to write down here, PV equals nRT. Now I'm going to start listing everything. I have to calculate I have my pressure I have to write down, my volume, my moles, my R value, and my temperature. So let's write everything down here. My pressure, it says here, is 1.89 times 10 to the third kilopascals. It says my volume is 685.0 liters. I am calculating here blank moles of helium, so that's what I'm solving for. R value, I'm in kilopascals, so that means it is 8.31 kilopascals times liters divided by moles times kelvins. Those are the units that it's in. And I got that right off my formula sheet. You don't have to memorize it. It's going to be there for you on your formula sheet. And your temperature is already right here in Kelvin, so we don't have to worry about a conversion. So 621 Kelvin. So now I can just plug all this stuff in. And on the ideal gas law, I like to just plug it straight into the formula just as it is. And you'll see why, because I can cancel my units off very easily this way. So my pressure here is 1.89 times 10 to the third, and this is kilopascals. My volume is 685.0 liters equals N, that's what I'm solving for. R is 8.31, and this is kPa times liters over moles times Kelvin. And then my temperature is 621 Kelvin. Right away, my Kelvins cancel. So that's important. So now I'm going to get rid of everything from this side. So I have to divide here and divide over here. So I'm going to divide by 8.31, and this is going to be kilopascals times liters. And when I divide this side by that, my moles are going to be up onto the top. So that gets rid of this whole statement right there. So now when I look here, and I have my 612 on this side here that I have to bring over, 621, sorry, 621. The Kelvins cancel off already, so this is no unit on this side here. So now if you look what happens, my kilopascals cancel and my liters cancel. So now I can plug this directly into my calculator. So I'm going to go 1.89, and this is times 10 to the third, multiplied by 685. I'm going to take that and I'm going to divide it by 8.31 times 621. So when I look at my significant figures, I have to be at 3 significant figures. So when I plug this in here, N is going to equal 251 moles of helium. So when you look at this, I have a large volume at 685 liters. And I have a high temperature. So what that all correlates to is I have a lot of moles of gas. I have 251 moles of helium. So that should be my final answer. So once again, you plug it into the formula, change it around to isolate your variable, and then plug it in. Let's look at another problem here. What volume will 12.00 grams of oxygen gas occupy at 25 degrees Celsius and a pressure of 0.752 atmospheres? So I am solving for volume and it's given me mass. That means I'm going to be dealing with moles, and the only gas law dealing with moles is the ideal gas law. So I can come over here and write that down. So I have PV equals nRT. So now I'm going to come over here to the side and I'm going to write down everything that is all my variables. That way I can just simply look at it and move forward with solving. So my pressure is 0.752 atmospheres. My volume is what I'm solving for here, blank liters. My moles, I'm gonna have to do a conversion here. So I have 12.00 grams of oxygen gas, which remember it's diatomic, it's 2 over 1. I need to get to moles. So I know that 1 mole of oxygen gas from my periodic table is 16.00, and there's 2 of them, so that's 32.00 grams. So that I can just plug this in really quickly on my calculator. So 12 divided by 32, and I am at 4 sig figs on all of it. So I'm at 0.3750. 0.3750 mole. Now my R, because I am now in atmosphere, I'm not using kilopascals, but I have the unit for that. Hopefully you took the time to write that down. So here I have 0.0821, and that's atmospheres times liters divided by mole kelvins. And then my temperature here is 25 degrees Celsius. So 25 degrees Celsius plus 273 equals. So now I'm going to be at 298 Kelvin. It is not degree Kelvin, it's just Kelvin. So please remember that. All right, so now I'm solving for my volume. So what I'm going to do here is I'm going to plug everything in. So my pressure is, I'll just do it right down here. So my pressure is 0.752 atmospheres. Then I have my volume. That's what I'm solving for. N is 0.3750 moles. My R is 0.0821, and that is atmospheres times liters over mole times Kelvin. And then my temperature is 298 Kelvin. All right, so right away I can cancel off my moles. Moles is gone. My kelvins, kelvin's gone. And that leaves me atmospheres times liters. So isolating, I'm going to divide this side by 0.752 atmospheres. Come over here, divide this by 0.752 atmospheres. Now my atmospheres cancels. So now I've isolated because this is gone. So now I'm solving exactly for my liters, and that's my volume. So let me plug this all in. So I have 3750 times 0.0821 times 298 divided by 0.752. And I am looking here at 3 sig figs. So my volume equals 12.2, and this is liters, 12.2 liters. So that is my final answer. So I can come up here and write that down, 12.2 liters. So I was given a bits of information, and I had amount of moles. They gave it to me in grams. That's no problem. I can easily convert, plug that all in, and I found my answer is 12.2 liters with 3 significant figures. So that is how you utilize the ideal gas law. So you have a worksheet that's going to be coming up due next week. I will have that loaded into Moodle for you here probably tomorrow or here in the very near future. I'll have that loaded in. So please don't forget to finish up the combined gas law worksheet that will be due later today. So thank you for watching. I will have another video that will be part 2 to this. All we did is learn the solve. Now we're going to learn the concept of an ideal gas versus a non-ideal gas. There's a differentiation there. So I'll have that coming up on Monday for us, our second virtual lesson for this particular section. We're probably 2 weeks out now from the test on chapter 14. So anyways, thank you for watching. Have a great day.